Before you do, all right. Okay, well, welcome everyone to the first TEPS seminar of the academic year. We're very pleased to have Candice Hansen joining us as our first seminar speaker. So I'll actually hand it off to, I believe, Isaac, who will give a much better introduction than I can.
Yeah, so Candice, thanks very much again for coming here to talk to us about JunoCam. So I've known Candice a long time in my career, almost the entirety, but she's been in the field for much longer. Currently, she's a senior scientist at the Planetary Science Institute, but she completed her bachelor's in physics and immediately went to JPL to work on the Voyager imaging team. And she was an assistant there who designed the camera imaging acquisition sequences for every flyby at Jupiter, Saturn, Uranus, and Neptune, which is a pretty impressive feat. That's really impressive. After the encounter with Uranus, there was a couple of years before it got to Neptune. So she started her master's at UCLA, and her thesis, an eventual Ph.D. thesis, was on the Triton's nitrogen, frost, and atmosphere. In 1990, she joined the Cassini mission as a co-I for the ultraviolet imaging spectrometer, UVIS, where she studied the Enceladus water vapor plume, and she won JPL's prestigious Ed Stone Award for outstanding research publication on that work. At the same time, she was serving as a deputy PI for the Mars Surveyor Program's 1998 Mars Polar Lander. It was ill-fated, but it was a really important role at the time. And since then, she's always been a Mars polar science person in my eyes. And she was the deputy PI of HiRISE, the very fantastic camera that's on Mars Reconnaissance Orbiter. And she uses that to study seasonal processes related to CO2 on Mars. And she also used that to become a co-investigator on the color and stereo surface imager system called CASSIS on the European Space Agency's Trace Gas Orbiter, another high-resolution camera. She's received numerous awards for, quote, exceptional leadership, exceptional scientific achievement, outstanding research publication, exceptional service, and technical excellence. She is now, today, she's going to talk to us about JunoCam and the fantastic science you can see behind her, a picture of Jupiter. Her talk is JunoCam, Images of Jupiter, A New Perspective. But before she does that, I just want to say that Candice was one of the very first people I met when I went to my first planetary science conference. And she's been an inspiration to me all along. She's a very welcoming person into the community. She likes to meet young people and learn from them. And for me personally, planetary science wouldn't be the same without Candice. And so thanks very much, Candice. Really appreciate you being here.
Oh, thank you, Isaac. I'm blown away. Thank you so much. Well, in order to get going here, I think I need to take over sharing the screen again. Yeah, so I guess you could, if you had to sum up my career, you could say scattered across the solar system. And I feel personally a bit like I've come full circle from my earliest days of working on Voyager, planning imaging sequences for Jupiter, the Jupiter flybys. And now I'm back at Jupiter, this time in charge of the camera rather than the assistant to the assistant to the assistant operating the camera. So what I'm going to show today are a lot of beautiful images of Jupiter that we've been taking with JunoCam. And okay, there we go. So I'm going to give like a very brief 2-slide intro to Jupiter just in case you've forgotten, if anyone has forgotten, a little bit about the Juno mission. I'll mostly focus on JunoCam's images because that's what I work on. I have thrown in a couple of science nuggets from some of the other cool discoveries that we've made. And I'll talk a little bit about Juno's extended mission, which just got approved. So for anybody who might have forgotten, Jupiter is the largest planet in our solar system. When you're looking at Jupiter, you're looking at an atmosphere, a very, very, very thick atmosphere. We don't even know, what the size of the core is really, although that is one of the Juno goals. The atmosphere is primarily composed of hydrogen and helium, but a lot of the coloration comes from sulfur compounds and methane and different mixtures like that. The dark and the bright stripes are called belts and zones, and the great red spot has been churning away for probably 400 years. Jupiter has 4 large moons that we call the Galilean satellites. Io on the left, covered with volcanoes. Europa, which will be the destination for the Europa Clipper mission, which will launch in 2024. Ganymede and Callisto. And Europa, Ganymede, and Callisto all have water ice surfaces. Io presumably burned its off long ago. That's a story for another day. So the Juno mission. Some of the important features, it's the first solar powered mission to Jupiter. The solar arrays are enormous. It's got 8 science experiments plus JunoCam. We don't actually count, and I'll get to that in a minute. It's a spinning spacecraft, and it's in a polar orbit. We launched in 2011. Took us 5 years to get to Jupiter, and we've been in orbit ever since. So we launched on just a gorgeous day in August in 2011. Fast forward to 2016. Something about space missions, things always happen on holidays. And so our orbit insertion was the 4th of July. The really sort of science enabling feature of this mission for the goals that we have is the fact that it's in a polar orbit. So all the previous spacecraft that have either orbited or flown by have been in the equatorial plane. And that is, and Jupiter is only tilted about 3 degrees on its axis. So that means that we've never really had a good look at the poles. You can see that this is a highly elliptical orbit. That actually was not our original intention. Our original intention was to wind up in a 14-day orbit rather than a 53-day orbit. The 53-day orbit was simply meant to capture the spacecraft into orbit around Jupiter. But yeah, we did that successfully. But when we went to get ready for our burn to bring the orbit from 53 days down to 14 days, we discovered a problem with the propulsion system. And there was enough concern that we could, blow up the spacecraft if we continued, that we decided what's not to love about a 53-day orbit. And so that's where we stayed. And the reason that it really didn't make that much difference, scientifically speaking, is that all of our data, most important data collection, happens when we're quite close in, close to closest approach. And we call that perijove. Closest approach is called perijove. And we talk about that as our perijove pass. So the way that NASA missions start is by laying out what are the science questions? What are the things that we want to learn? Once we figure out what are the questions we're asking, what do we want to learn, then we say, okay, what measurements do we need in order to answer those questions, and what instruments will provide that data. So once that sort of discipline once we did that for Juno, it really became apparent that the questions that you see on your screen don't actually require a camera, at least not a visible imager. And so we are carrying a magnetometer, we're carrying a microwave instrument, ultraviolet instrument. But because we really didn't have to have a visible imager to answer our science questions, it sort of freed us, in a sense, to do other things. And so my boss, the principal investigator, Scott Bolton, said, we are not flying to Jupiter without a camera. And so we decided what we're going to do with our camera is give the public an opportunity to participate. So not just to sit back and, browse things on the internet, but to actually be a part of the mission. And so that was one of our key design drivers. When we said, okay, what is unique about this mission? Clearly it was the views that we would get of Jupiter's poles. And then that's what drove the camera design, because it's a spinning spacecraft. There's no real ability to point. So we needed to take in the entire pole in one image. That set the size of our optics to be a 58-degree wide field of view. The fact that we're on a spinning spacecraft has additional challenges when you're trying to take a picture and you're actually in motion at the same time. And so we went with a design called the push frame imager, and we put the spacecraft spin to use rather than fighting it. So these first two images collected on Perijove 1, the Perijove 1 pass, show the South Pole and the North Pole. And this was really the first view ever for humankind of the poles of Jupiter. And one of the first things that we discovered is that there are cyclones arranged in a kind of a geometric pattern around each of the poles. And so I'll say more about that in a little bit. Because our sort of vision was to involve the public in the actual camera operation, we basically said, okay, what does a more of a classic traditional imaging team have to do? And we parsed that into these 5 components: planning, talking, making decisions, processing the data, and then analyzing the data. So we set up five portals where the public could get involved, depending on what their interest was. I will say right now, I'm only going to talk about planning and image processing. The other 3 were not as successful, but those 2 have been fabulously successful. So this is an example of our webpage where we have invited amateur astronomers around the globe to input their own images from their own telescopes in their own backyards. And some of these are phenomenal. The possibility to stack images now is just amazing, the kind of detail that you can get. And so they upload their original data, and then we turn it into a cylindrical map that gives us a snapshot in time of Jupiter. And the reason for doing this, of course, is because the atmosphere is so dynamic that without their help, we would actually not know what we were going to see on the next Perijove pass. So we use this data to help plan our image sequence of what we're going to collect on any given upcoming Perijove pass. We also get a lot of help from the British Astronomical Association, the Jupiter Division. This is sort of where pros and amateurs come together and, basically talk Jupiter. And so a lot of the historical knowledge of what's going on in the atmosphere, what colors, the equatorial zone, those sorts of things, takes place in this sort of community. The image processing page has 3 different galleries. We post our raw data on the upper gallery that you see where it says most recent from JunoCam. That's where we post our images after each Perijove pass. The bottom gallery, which says most recent from the public, is where people go to post what they have done with the data. And it's amazing. And that will be really the bulk of my talk. in the middle is the kind of featured submissions, could also be labeled Candy's favorites. It's just a nice collection of the different sorts of things that people have contributed. And I've been putting the website up as we've gone along, just in case there's amateur astronomers in my audience or amateur image processors. Actually, let me pause for a second here. Are there any questions so far? Okay, well, I'll just go on then. But please actually do feel free to interrupt me if you want to ask a question. Hopefully you're not all on mute at the moment. Okay, so we upload raw versions of the image. And so that's what's down here in the lower left corner. It's a push frame imager, as I said, so we get stripes of red, green, blue, red, green, blue, red, green, blue as the camera, as the spacecraft spins and the camera crosses Jupiter. And so we post the raw data because some of our contributors like to start there. We assemble monochrome images through the red, the green, and the blue filters in case that's where someone wants to start. And then we do a map projected basic color reconstruction. And that's where we'll start. So it gives us 3 levels for people who are interested. And so using some, readily available image processing programs like Photoshop, for example, this is the kind of processing that people do. And it's really, we don't put any advice or restrictions. We just say, knock yourself out and please post it back, post your masterpiece back on our website. Don't just, stick it on your Facebook page or Flickr or whatever. Share it back with us. That's our only request. I'm going to show you a lot of exaggerated color. So I wanted to start by showing something that's closer to true color. And for each of the images that I show, I will show who did the processing. So in this case, it's Bjorn Johnson. Bjorn prides himself on getting the color right. So that this is, if you were flying along with the spacecraft, you would see this subtle pastel kind of hues. A few more words about the geometry. Our pictures are taken, most of our pictures are taken in the 2 hours right around Perijove. So we have our best polar views incoming, then 2 hours later coming over the north and outbound over the south. And this whole Juno goes from the north to the south in just 2 hours time. So we are really flying as we make that Perijove pass. And then your celestial mechanics will tell you that we hang around out here at Apogee for quite a long time. And these actually are 1-day ticks on the orbit. So you can see how much time we spend out at Apogee and how very little time we spend in close to Perijove. The other thing to point out in this diagram is that for most of the mission, we were getting nowhere close to any of the Galilean moons. So this, the orbit of Callisto is out here, then Ganymede, Europa, and Io. And as you can see, our trajectory was not even close to these moons. Another word about how to understand what you're seeing in these pictures. When we're over the north or over the south, we're standing off at a distance. So we see all of Jupiter in our image on the left and on the right here. But in the middle, when we're really close, all we are seeing is this little arc of the surface. And so we're so close to the clouds. We're just, this distance here is about 3,000 kilometers. So we're really just skimming the cloud tops. And so when we put all of the images together from one perigove pass, we get a lot of data over the North Pole, as much as is illuminated, because of course half of the planet is it's nighttime, so it's dark. And then we get our swath of high resolution images really over just one sort of longitude swath. And then we get quite a bit of the southern hemisphere as we leave outbound. And you can see how different that kind of perspective is from the classic Earth-based observer kind of view. So here's an example of how that perspective changes as you see the full northern hemisphere, but then coming in closer and closer and closer, you can see how this storm appears to change size, but in fact, we are just that close that it looks gigantic. Now, I have to say, we did reach out to the image processing community, and very deliberately. What I did not expect was that artists would find us. So we did not make any effort to reach out to the art community, but they found us, and their contributions are spectacular. Quite often, one person will do the first processing, another one will do another layer, and then one of our artists puts their personal touch on it. And so you can see in this transition, this is the image that we posted. Gerald Eichstätt is one of our most valuable contributors. He removes the photometric function that goes from the limb to the terminator, flattens out that brightness difference. Sean Doran does incredible digital image processing. And then this picture on the right is actually an oil painting by Lucy West. And, I am not an artist, but I have to say, I love seeing Jupiter through the eyes of artists. It's really kind of changed my whole perspective on the beauty of that planet. And this is like one of my all-time favorites, and it's the one that's in my background today. This one, the title of this artwork by Rita Najm is called Roses on Jupiter. Okay, getting back to some of the science, I said earlier that one of the first things that we discovered is that there are circumpolar cyclones. And so there's a cyclone at the pole, both the North Pole and the South Pole. And then in kind of a geometric configuration, we have the cyclones around that central polar cyclone. And so in the case of the northern hemisphere, 8, and over, we've been in orbit now 5 years, and over the course of those 5 years, there are still 8 circumpolar cyclones at the North Pole. We know that they're cyclones because with our image data, if you put it into a little time-lapse sequence, you can see the direction of the rotation. So our little outreach camera is actually has turned into a science instrument. And, because half the planet is in nightly darkness, the diurnal darkness, it takes us at least 2, if not 4 perigoves to actually assemble the entire collection. But you can see it here. There's the central northern polar cyclone, and then the 8 circumpolar cyclones surrounding it. And the actual configuration flexes, but there's always 8. And then over on the left, another artistic rendition of one of those circumpolar cyclones. And I will say, there is this amount of detail in the image, but the artistic treatment really brings it out for our eye-brain combination. So I'm going to take you now on a tour from the north to the south of Jupiter. And so this is one of the images taken at more northerly latitudes. So we are still seeing the circumpolar cyclones up here, but you're now picking up this region that's called the folded filamentary region. And this tends to have big, massive structures that rotate in a sort of a cyclonic sense, but they're very sort of, I don't know, blobby, not very structured. And then lots of cyclonic and anticyclonic circulation as you move further away. And so here's one of our views from Sean Doran. This is taken at 62 North. And this is one example of the beautiful sort of folded filamentary cloud structure. This is moving down a little bit in latitude. So we start to see the more familiar belt zone structure, but then also the storms that show up in that belt zone, in that, you know, sort of generic belt zone structure. You start to see the individual storms. And here's another example from Perijove 30, the big circulating storm up here, and some more of the folded filamentary region. And this is still in the northern hemisphere. One of the cool things about getting really close to Jupiter is that you start to see a lot of structure in areas that to ground-based or even Hubble Space Telescope images appears rather bland. And so now we're at about 20 degrees north. This is the north equatorial belt in here, the orange band. And you can see the amount of detail now, the amount of structure in the cloud is not visible without this kind of resolution. An interesting piece of history, one of the previous missions called Galileo sent a probe to figure out the composition of Jupiter's atmosphere by diving into it. And one of the things that was always very perplexing was that the signature of water was extremely low, much lower than anyone expected. And sort of after the fact, they reasoned out that the Galileo probe had actually gone into a hotspot, an area where there wasn't very much water because of the high temperatures. And so here's an image from JunoCam of an actual hotspot. It doesn't look that remarkable, but basically you can see how it correlates on the left-hand side with data at 5 microns. And you can see in the 5 micron data that this is actually very, very warm region. Because of the sort of broad invitation that we sent out to not only the public, but also to our colleagues, a lot of science is and can be done with JunoCam images, even though we don't have a classic imaging team, because we post our data almost immediately. Other scientists around the world can just grab the images and start to analyze them. And so this is a region, it's called the STB specter. And with our data, we were able to establish the circulation pattern. The imaging was done by, the image processing was done by Gerald Eichstädt, the analysis by John Rogers, and now the professors, the scientists at the University of Basque in Spain are analyzing this particular flow regime. And we're learning more about the dynamics of Jupiter's atmosphere. Continuing on my tour from north to south, we're now down to the South Tropical Zone, the region where the Great Red Spot resides. And you can see these images on the right that the Great Red Spot has actually been shrinking. The top image is from 1995. The bars show you how much the size has changed between 1995 and 2014. Well, interestingly, the size of the cavity, or whatever it is that the Great Red Spot resides in, is about the same. It's just the spot in the center of the Great Red Spot itself that has been shrinking. And so in 2014, we were actually a little worried that it might disappear before we got there. But fortunately, that did not happen. Just to show you how wonderfully useful all of our amateur contributions are. I don't have to tell you anything about the scale because Tony Rice and Jason Major contributed this comparison of the United States to the Great Red Spot. And in fact, the Great Red Spot is big enough to swallow the Earth. Here's what it looks like, and this is actually true color. So maybe we should call it the Great Orange Spot. But in any case, this is not enhanced. This is really how it looks relative to its surroundings. So it's really distinctly different from the surroundings. And one of the things that we were fortunate to capture in our images is these tendrils. You can see these tendrils of the orange material being pulled away, kind of like cotton candy being pulled away and swept into these surrounding turbulent regions. And, you know, so one question is it just being eroded away over time? Don't know, but it certainly looks like that's a possibility. So here's a collection of all of the images of the Great Red Spot that we've gotten. Because we don't always fly over this longitude, we don't see the Great Red Spot every time, but we had a close pass on Perijove 7. Great data again in Perijove 12. That's the one I was just showing you with the tendrils being pulled away. And as time goes on, we've seen it again and again. And so not only the Great Red Spot, but we can also see what's happening with the turbulence in front of it. We can see when one of the other storm features catches up with it, and so on. This was one of our, I think, really best examples of the amateur, the pro-am collaboration that we've got going. Clyde Foster discovered this little bright spot here in the methane filter of his image that he took from his telescope. And so he really quickly broadcast its existence. It had just shown up. So we saw it right when he saw it right when it first was formed, this whatever eruption, whatever you want to call it. It's bright in methane. That means it's high. About 2 or 3 days later, we had a pass with JunoCam, with Juno, and we were able to get this image. I hope you can see my cursor of Clyde's spot. And by this time it had broadened out a little bit, and you could see there's sort of 2 sides to it. And in the methane, we have a methane filter also, and it looks like this down at the bottom. So it was just beautifully framed between the Great Red Spot and one of the anticyclonic white ovals down below. The next time that we had a Perijove pass over that longitude, lo and behold, the Clyde spot has now morphed into a folded filamentary region kind of structure. So it's spread out, it's gotten more complicated. You can see it's gotten quite a bit larger. This is oval BA over here. We call these the string of pearls. These white ovals always occur at this latitude, and there's usually 8 or 9 of them. So we caught 3 in this particular image. But it's just remarkable how this little storm has evolved into this big feature. And so, you know, everybody's puzzling over that now as to what is the evolution that led to that. Now down at 49 South, we got this this beautiful image that we, of course, immediately dubbed the dolphin. There's no doubt that about the dolphin and the waves, but I've heard lots of descriptions of this thing on its tail. Is it a dragon or a sea monster? What in the heck is pursuing that dolphin? And this is what how you might imagine yourself if you were on a spacecraft and making a pass by Jupiter. You might pull out your cell phone and try to get a picture. Okay, moving now even further into the southern hemisphere, 58 degrees south. You can see, again, this is the string of pearls, these white ovals here. And you can see the south also has regions with this bands of the folded filamentary structures. And this is another one of my favorite artist renditions of this area. Here's a good view of, on this particular Pear-Jove pass, which Pear-Jove 33 was very recent. That was just this last April. And so the string of pearls had lined up really nicely for us. There's oval BA. This was called, I think, white spot 6, and then it was called dark spot 6 because these storms tend to change color and size, and the amateur astronomers keep track of really all of that. There are 5 circumpolar cyclones in the south, plus the 6th one right in the on the South Pole. And you can see they're spread around here. And the thing in the south is that there's always a gap, and that's what this little X is. And there was one Pear-Jove pass where another cyclone had snuck in, but by the next one, these two had closed ranks and kicked it out again. So it's a very exclusive little club. And that's been the source of a lot of research too, is the dynamics and the stability really of this configuration. Okay, I'm going to pause again, and maybe somebody can say something so I can just be sure you're all still there.
Yeah, Candy, we're here. Just
Okay.
enjoying the beautiful images in your description.
Yeah. Are there any questions?
I do. Very quick one. My name is Regina. I'm from York University. I'm a space engineer, and I look at the images from space, but to look for debris in an Earth orbit, not too far in Juno and whatnot. So I'm really not a scientist, to be fair, but I do work with the artists, and this has been completely motivating, amazing, and I'm just mesmerized. But one of the challenges that we face working with the scientists in the group is that sometimes the result that we see from scientists may not bear some of the scientific artists may not be seen as the scientific sort of like interpretation of the data that we have, and artists don't necessarily interpret the data we present in the same way. So we
Right, and that,
go ahead.
yeah, I would not advocate doing science from one of our contributions from one of our artists. It's really more just to appreciate that we all bring different talents to bear and different perspectives. Although I will say the color enhancement, our eye-brain combo loves color. And so I will go back and forth between the original images and the color, the exaggerated color. And quite often I'll see something in the color and I'll go back to the original and go, oh yeah, that was there. I just didn't notice. And so I think that that's part of the advantage. But yeah, I would not tell a scientist, oh yeah, go grab this particular artistic rendition and figure out the photometry of the clouds. that would be perilous.
Another personal comment, probably is not relevant to everyone in the group, is that it's really hard to find funding. We have so many ideas of like getting citizens involved, working with amateur astronomers, and getting the whole knowledge and passion out there to share with general public. But there's not many funding opportunities. So we sort of do it for our own benefit and our own interest, but
Yeah.
it's been a challenge. So I'm just throwing the idea out there, but
Yeah,
the
no,
images are
that's
just
very
amazing.
true. That's very true. And I do try, for the people that I personally interact with, I always try to tell them how much we appreciate this. It's literally a donation of their time. Okay, I am just gonna really quickly give you some snapshots. We call them nuggets of some of the other findings. I'm not going to spend a lot of time on these, or I'm going to completely run out of time. But just to show you some of the other kind of science results that are coming out of the Juno mission. One of our goals was to map the magnetic field. And you could just take a glance at this and say, oh God, that doesn't look dipolar at all. And so it's obviously much, much more complex. And so we're mapping the field strength and, doing our best to understand what's going on in the interior that is creating the magnetic field that the spacecraft is flying through. One of the science goals was to study the aurora. And so we have now learned a lot about the interaction of the Jovian magnetic field with the Galilean satellites. And it goes back and forth. The moons influence Jupiter, and Jupiter influences the moons in the sort of state of their whole charged particle environment. This is water abundance was one. I have to say, we have not actually achieved that goal quite as well as we thought we would, because of the fact that water and ammonia are not well mixed. And so you have to be able to take out the signature of the ammonia to get the signature of the water. And there's a lot of complexity to that. So I expect that with the data that we'll be getting in our extended mission that I'll describe in a minute, that at that point we'll have what we need to really figure it out. I've been showing you all these beautiful pictures of the clouds and the belts and the zones. There's a zonal wind structure that goes along with that, and with winds blowing east and west. And the question was, is this a very sort of superficial atmospheric phenomena, or just how deep does it go? And from our gravity field data, we're able to show that it's actually quite a bit deeper than people thought. Just to give you a taste of the future, we just got our extended mission approved just in the last few months. And so what you see here is the evolution of the big elliptical orbit that Juno's been in. And because of the oblateness of Jupiter, its gravitational influence on the spacecraft orbit has been such that apogee has been moving south. And so you can see how we call this the orbit pedal. You can see how the orbit pedal's been moving south. And what's happening as it continues to move south is you can see that we have begun to cross the orbital plane at the distances of the moons. And with close flybys of the moons, specifically Ganymede and Europa and Io, we're actually bringing the orbit period down from 53 to now we're actually into 42 days. And likewise, the perigee point has been moving northward. So our very first perigee was right at close to the equator. It was at 4 degrees north, moving northward. Perigee 34, which was in June, was at 28 degrees north. And by the time we get to 75, we'll be way up at 63 degrees north. So we'll be getting close-ups of the North Polar region. Unfortunately, that means our south polar data is going to get further and further away. So the fact that we can now cross the Galilean satellite orbits means that we can time our passage to actually get close flybys. And you can see we only get one or maybe two, but they're brilliant. And so for Ganymede, we had our closest approach in June, and now we're into these orbits here. We will get close to Europa next year. And then we have two close passes of Io that will use exterior of Io and try to understand more about the magma chamber that powers its volcanoes. So we have that to look forward to about 2 years from now. So our first image of Ganymede from JunoCam at this, we were 1,000 kilometers above the surface, and we got just absolutely stunning detail. So if we only had to make one pass, at least it was a really awesome flyby. It turns out we thought that we would not really be improving on existing data, but the existing data in this particular area came from Voyager. And it turns out that some of the Voyager images were a little bit smeared because Voyager is a 3-axis stabilized spacecraft, and it was built in the era before reaction wheels. So, you know, depending on when a thruster might fire, you could get images that were smeared. So in fact, even though we don't have major new discoveries coming out of these images, we are going to really substantially improve the existing maps. And then just to give you a couple of close-ups, this is the crater Tross, one of the youngest on Ganymede. You can see the bright crater rays, the ejecta blanket. And then Ganymede has dark terrain, and that is dissected by bright grooved terrain. And so we're hoping with our full complement of learn more about these structures. And just again, making the point that a lot of times what you see in realistic color, which is the top image, you really see quite a bit better when the colors pop. And so anyway, there's the pleasure of looking at those images. So I will end here, and I think hopefully with plenty of time for more questions. Let me just circle back to the citizen science for a minute, because I'm also involved with a citizen science project studying Mars seasonal fans that show up on the seasonal polar cap. We set up the whole citizen science project ourselves, we being me and a couple of other members of the HiRise team. We used Zooniverse, which is funded by a consortium of institutions that think that STEM is important and citizen science is important. And then we started writing proposals to the NASA RNA research and analysis programs to actually be able to analyze the data. So the point I try to make to NASA headquarters whenever I have an opportunity is that scientists bookend citizen science projects. You need the science community to pose the questions and say what data, what measurements, what analysis needs to happen. Then you need scientists to come along at the end and say, okay, now that all these measurements have been made and this data has been analyzed, what is it telling us? What are we learning? And so we actually did get some funding for that. Okay, if everybody has had a minute to jot down this URL down at the bottom here, I am going to stop sharing. Okay.
Fantastic. Thank you so
Any
much.
other questions?
Oh, we have a few questions actually, so I'll just go with. Oh,
Thank you.
Bravo.
Thank you very much.
Leah, how about you first?
I didn't actually have a question. I was just
Oh,
clapping, but I mean, I can ask one anyway. I can just, what are you most excited about as far as the upcoming studies that you mentioned of things you're looking at? What do you think is the thing that you in particular are most excited about?
Well, you know, when I joined the Juno team, Scott came to me because of my expertise in imaging systems, and not because I had any expertise in gas giants, and because my, you know, my love and my background is more icy satellites and the South Polar or the polar ices on Mars. And so I've been like the lone satellite scientist on the project for years. And so the fact that we are now getting data on Ganymede, I will say my the data I'm most looking forward to is going to be our images of Europa next year. But just to me, just the new images of the Galilean moons is like, woohoo!
That's gonna be very cool to see. Did you find anything really surprising about the imagery that JunoCam is sending back? Something that really caught you?
Yeah. So one of the things that has captured my attention are there's some very, very tiny storm features that we see along pressure ridges. And we call them pop-up storms because they seem to, or pop-up clouds is probably better. They seem to form in particular regions and not others. And so not being an atmospheric scientist, I didn't really expect to get so scientifically intrigued by something, but these little storms, you can actually measure how high they are because they cast little shadows, and they're actually not that small because it's Jupiter. They're 50 kilometers. They just look tiny. But yeah, that has been the thing that has sort of captured my imagination is how do they form? Why do they form? Where they form? And why didn't we notice those before? That was the first thing. When I first saw the images, I thought, well, that's weird. I've never really seen those or thought about those. And so I went back to the Voyager data, and sure enough, they are there. There's little bright white spots. But the difference is that JunoCam has this 58-degree wide field of view. So you capture, and Voyager's was a half a degree, right? So you capture this tiny, tiny little region of Jupiter that has a couple of bright spots in it. That's not so remarkable as when you've got all of Jupiter and there's an entire band of them. And so, and that was true of the Galileo images also. Then the high resolution camera only ever captured a tiny area of of Jupiter. And so you didn't see the whole context of these pop-up clouds. So that's, okay, so now I'm turning into a giant atmosphere scientist because this pot of gold landed in my lap, literally, and I'm intrigued. I will say my PhD advisor on the day that I got my dissertation, got my PhD, he told me, he said, this is your license to do science. Do not feel obligated to do what your dissertation was on. And that was probably the best piece of advice I've ever gotten because I've had this really, wide-ranging set of opportunities. And so really, I think the bottom line is that in this field, you're always a student. You are always learning something new. And when I started working with the Cassini ultraviolet team, I really did not know that much about ultraviolet spectroscopy, but I thought, I am working with a team of experts, world-class experts. I will learn at their feet. And so I treated every team meeting like a seminar.
Yeah, that's a great inspiration. There's a lot of students listening and ones that'll watch the video, so that's a great thing for them to hear too.
Do we have any other final questions for Candy before we finish off? Looks like no. So again, Candy, I'll say thank you so much for the wonderful presentation. This is
You're
a
very
great way
welcome.
to start off the academic year, the TEPS seminars for the academic year. Yeah, I'll wish everybody a good evening, and we'll reconvene next month. Okay.
Bye, everybody.
Bye.
Thank you.